Linear Independence and Basis is the title of section 4.2 in Topics in Algebra by Ian Hastings. Now in this video, we are going to have concepts on linear combination of vectors and linear span of a set of vectors. Now are we familiar with the word linear combination? Now if we consider this yellow shade along with this blue shade, then we know that it gives us a green shade, and a linear combination of this yellow shade with this red shade gives us orange shade. And above all, everybody knows that suppose we consider 3/4 of milk and 1/4 of our coffee decoction, then we can have a cup of coffee. So we are all familiar with the word linear combination. So now we shall have the mathematical description of a linear combination of vectors. If V is a vector space over a field F, and if V1, V2 and so on Vn are in V, then any element of the form alpha 1 V1 plus alpha 2 V2 plus and so on alpha n Vn, where alpha is a scalars from the field F, is a linear combination of V1, V2 and so on Vn over F. For example, if you consider V to be R3, collection of all ordered 3 tuples with entries from the field of real numbers, and if we take V1 to be the ordered triplet 1, 2, 3 and V2 to be another ordered triplet, say 1, 0, 1, then we can have this ordered triplet minus 2, 4, 2 as a linear combination of V1 and V2, and exactly it is minus this ordered triplet minus 2, 4, 2 is 2 times V1 plus minus 4 into V2. Now we have the definition of linear span of a non-empty subset of a vector space V. It is denoted as L of S, and it is nothing but the set of all linear combination of finite sets of elements of S. So it is this notation that we use to denote our linear span of S, L of S. If S is this collection, remember that it need not be a finite collection. It is any non-empty subset of a vector space V. So this consists of the set of all linear combinations of the form alpha I Vi, where I range over 1 to n. This combination, when we consider, that should be finite combination. But these vectors, they range over any non-empty subset. So this alpha i's are from capital F. Now as such, L of S is not finite. So but what we notice further is that this S is properly contained in L of S. That is, by taking alpha 1, see when we consider this as say alpha 1 V1 plus and so on alpha n Vn. So by choosing alpha 1 as 1 and the rest of the scalars to be 0, our V1 will be present. By choosing alpha 2 to be 1 and the rest of the scalars to be 0, then we get V2 and so on. So it's very obvious that S is definitely contained in L of S. Now in the next lemma, we are going to prove that L of S is a subspace of V. So we shall take S to be this collection V1 etc. Vn, then L of S by definition is nothing but the set of all elements of the form summation alpha I Vi, I range over 1 to n, and alpha i's are from capital F. Then S is being a subcollection in L of S. L of S is definitely a non-empty subset. Then in order to have L of S to be a subspace, we know that if you consider two elements U and V in L of S, we have to show that lambda U plus mu V also to be a member of L of S, where lambda and mu are members of capital F. So if we consider U to be a member of L of S, then we can write U in this way. And V being a member of L of S, already we have considered, we can write it in this way. Now we shall take lambda mu to be in F and consider this lambda U plus mu V. So that we have this step, that is, you are replacing your U by this and V by this, so that the resultant you get like this. Now in this, we'll have to have, see there are two numbers m and n. We'll have to be certain that whether m is greater than n or n is greater than m. So we are taking here m to be greater than n. So we have these the sum of the elements being written in this way. So ultimately it's a linear combination of finite sets of elements of capital S. and therefore lambda u plus mu v should be a member of L of S, and therefore L of S is a subspace of V. Now, if you consider this next question is L of S, can it be equal to V or should it be only properly contained in V? In some cases, we can have L of S to be properly contained in V. In some cases, it can be the whole of V. So, suppose I consider V to be the collection of all ordered pairs with the entries from the field of real numbers, and V1 is taken as ordered pair 1, 2, and V2 is taken as the ordered pair 2, 4. Then if we take S as the collection V1, V2, then L of S is properly contained in V. For the reason that 5, 4, the ordered pair 5, 4 is in V, but it is not there in L of S. And therefore, L of S can be properly contained in V. But there are cases, as it is mentioned in this example, when we consider V to be R3, by taking E1, E2, E3 as ordered triplet 1, 0, 0, 0, 1, 0 and 0, 0, 1, and taking S as the collection E1, E2, E3, then L of S, when we consider the linear combination of these vectors, when we simplify this, we get that to be ordered triplet alpha 1, alpha 2, alpha 3, where this alpha i's are from the field of real numbers is nothing but the entire V. And in the same way, if you consider collection of all ordered n tuple, okay, where each component is from the field F, and by taking S as this collection E1, E2, E3 and so on, En, where E1 is ordered n tuple with the first component 1, the rest are 0, and E2 is again ordered n tuple with the first component 0, the second one 1, the rest are 0, and En to be again an ordered n tuple in which the nth component is 1, the rest are 0. Then we can easily see that this L of S is the whole of V. And if we consider V to be the complex numbers, which is written as the set of all A plus IB, where A and B are real numbers, then A and B are real numbers here, and S is taken as the set with 1 and I, then we can easily see that this L of S is the whole of V. And collection of all polynomials of degree n minus 1 or less, then in that case also, by taking S as the set 1, x square and so on, x power n minus 1, we see that L of S is the whole of V. And if you consider f suffix 2, the collection of all 2 cross 2 matrices, then in that case we can see that if I take my S as 1, 0 in the first row, in the second row 0, 0, and the second matrix 0, 1 in the first row, 0, 0 in the second row, and in the third matrix 0, 0 in the first row, and in the second row 0, 1, and in the last matrix 0, 0 in the first row and 1, 0 in the last row, then we can easily see that L of S is the whole of V. In this lemma, we will prove that L of S is a subspace of V. Let S be the collection V1, V2, V3 and so on, Vn and so on. Then L of S by definition is all those elements of the form summation I ranging from 1 to n alpha I Vn. That is the finite linear combination where alphas are from capital F. Then as S is properly contained in L of S is non-empty subset of capital V. Now, what is the condition for L of S to be a subspace of V? If I consider two elements U and V in L of S and lambda and mu to be in F, where we have to show that lambda U plus mu V to be a member of L of S. So now because U is a member of L of S, U can be written as the linear combination of V1 etc. Vn. A finite collection we have to consider. So U is alpha 1 V1 plus and so on alpha n Vn, and the same way because V is a member of L of S, V is again linear combination of finite sets of elements of capital S. So we shall take it as a beta 1 V1 plus and so on plus beta m Vm. Now we will consider lambda U plus mu V. So just replace U and V by this expression so that we will have lambda alpha 1 V1 plus and so on alpha n Vn plus mu into beta 1 V1 plus and so on beta m Vm. Then because we have two integers m and n, either m should be greater than n or n should be greater than m, or both of them are equal. So here we will consider m to be greater than n. Then we can collect the terms containing v1, v2 and so on, vn together, and then we can have the remaining, the linear combination, which consists of vn plus 1 and so on vm. So here delta I stands for this expression, and where your my I range from 1 to n. So it's a linear combination of finite sets of elements of S, and therefore lambda u plus mu v belongs to L of S. Hence L of S is a subspace of V. Next we see that this L of S can be in some cases a proper subspace of V, or in some cases it is the whole of V. Now for example, in the collection of ordered pairs where the entries are from the field of real numbers, if you consider V1 to be say ordered pair 1, 2 and V2 to be the ordered pair 2, 4 and S to be the set with V1, V2, then LFS is properly contained in V, for the reason that if you consider ordered pair 5, 4, which is definitely present in V, but it is not there in LFS, because you cannot write this 5 and 4 in terms of V1 and V2. So this element is not a member of LFS, but it's a member of V, and therefore in this case LFS is properly contained in capital V. Now here are a few examples in which LFS is the whole of V. If we consider V to be collection of all ordered triplets, and E1, E2, E3 is taken as the ordered triplet 1, 0, 0, ordered triplet 0, 1, 0 and ordered triplet 0, 0, 1, and S is taken as the set consisting of E1, E2, E3, then LFS will be the whole of V, because LFS we have by the definition the linear combination of elements from S. There are only 3, so we have written this as alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3, alpha I belongs to capital R, that is the field of real numbers. And this is rewritten in this way, and that is exactly your capital V, that is R power 3, that is collection of all ordered triplets. Now this is the generalization of the previous one. So we have V to be collection of all ordered n tuples with components from F, and suppose we have S to be E1, E2, the set consisting of E1, E2 and so on En, where E1 is the ordered n tuple with the first component 1, the rest are 0. In E2 the second component is 1, the rest are 0, and so on En, the nth component is 1, the rest are 0. Then LFS equals capital V. Now in the case of C, which is the set of all elements of the form A plus IB, where A and B are real numbers, by taking S as the set consisting of 1 and I, we can easily see that LFS is the whole of V. And if you consider V to be V suffix n, the collection of all polynomials of degree at most n minus 1, then in that case we have our S. If we have it as say 1x and so on x power n minus 1, then also LFS is the whole of V. Now the last one, if V is considered to be the collection of all 2 cross 2 matrices, which we denote as F suffix 2, where Aij's are from capital F, by taking S as these 4 2 cross 2 matrices, then we can easily see that LFS to be the whole of V. So if V equals LFS, then we say that S spans V. So in all these cases, S spans V, and S in each case is given in the example. That is S is in this case E1, E2, E3, and in the case second case S is E1, E2, E3 and so on E, and here 1 and I are the members, 1 x, x square and so on x power n minus 1 are members here, and here these matrices are the members of capital S. So in all these cases we say that S spans V. Next we have this lemma which states that if S and T are subsets of V, then S is contained in T implies that L of S is contained in L of T. L of S union T is equal to L of S plus L of T, and L of S is L of S. Now we do the first subdivision. we shall take S to be the collection S1, S2 and so on Sn, and S to be contained in T. Now if you consider small s belongs to capital L of S, then S is written as the linear combination of elements of capital S. So we have such an expression for S, and where Si belongs to capital S and alpha I belongs to capital F. Now since S is contained in T, Si should be a member of T. S is contained in T. See, strictly speaking, these are all members of S only, but this being contained in this, that is our assumption, we must have Si to be in T also, and therefore S belongs to L of T, and hence L of S is contained in L of T. Now for the second one, to prove that L of S union T is L of S plus L of T, we will prove that L of S union T is contained in L of S plus L of T and vice versa. So we shall take S in L of S union T, then S can be written as the linear combination of elements of S union T, which we shall take as S as those elements, so that we can have small s to be written in this way. Now without loss of generality, we are going to have, see, these SIs are from S union T, there is no doubt in that, but we are going to allocate among the n elements, say first m elements are in capital S. So nothing wrong in assuming this. So without loss of generality, we are going to take this and the remaining to be in capital T. Now obviously the linear combination of the elements of capital S should be in L of S, and the same way the linear combination of elements of capital T should be in L of T. So when we consider S, which is written already here, we can group the elements in this way. It's an obvious member of L of S, and this to be obvious member of L of T, and therefore S is a member of L of S plus L of T. So L of S union T is contained in L of S plus L of T. We shall name this as statement P. Now by the first subdivision, L of S to be contained in L of S union T, and L of T is contained in L of S union T. So this implies that L of S plus L of T is contained in L of S union T. Name that as statement Q. So from the statements P and Q, we conclude that L of S plus L of T is L of S union T. Now to prove the third one, we claim that if W is any subspace of V, then L of W is the whole of W. Now let W be any subspace of V. Let U belong to L of W. Then U can be written as the linear combination of V1, V2 and so on Vn, say alpha 1 V1 plus and so on alpha n Vn, where Vi is range over capital W and alpha I are members of capital F. Now since W is a subspace of V, U must be a member of capital W. So L of W is contained in W. We started with U in L of W. We have got U to be in W, and therefore L of W contained in W. But we know always that W is contained in L of W, and therefore L of W is the whole of W. So this is possible because W is a subspace. Now we know very well that this L of S is a subspace. So by replacing W by L of S, we conclude that L of S is L of S. So that proves the third part of the lemma. Next we have the definition of finite dimensional vector space. So a vector space V is said to be finite dimensional over F if there is a finite subset S in V such that V is equal to L of S, that is S spans V. If S is a finite subset of V spanning V, then V is called finite dimensional vector space. Now all the vector spaces mentioned in example 4.2.6 are finite dimensional, whereas Fx, the collection of all polynomials, here we don't mention the degree. So all polynomials, this is not finite dimensional vector space. Now we have in example 4.2.6 all this. So in this case we have V to be S consists of finite number of elements and S spans V. So V is finite dimensional vector space. In this case also S is finite, L of S equals V. So V is a finite dimensional vector space. Here again, S is finite, L of S is the whole of V, and therefore V is finite dimensional vector space. And here S consists of these elements, and L of S is the whole of V. So we have here also V to be finite dimensional vector space, and the same way the last one. So with that, this video concludes. So in the next video, we will be seeing the finite dimensional vector space when it is called as a dimension. I mean, when do we say the dimension of V in that to be some number? So that means for which we need to know the definition of basis. So that is discussed in the next video.